Generalized linear models for binomial data using Navure. To illustrate this procedure, we will use the test data set named wheat fungus disease. Locate this file in the test data repository. It contains the result of an experiment to compare the change over time in the incidence of a fungal disease in a wheat crop. A comparison is made between 13 fungicide treatments. Treatment 1 is the no fungicide control. The experiment was conducted in a randomized complete block design with 4 replications. In each plot of a block, a sample of leaves was examined for signs of infection and the number of infected leaves, and the size of the sampled leaves were recorded. The plots were sampled at 15, 25, 37, and 44 days since emergence. These data are called longitudinal because the same plot was observed several times over time. This type of data requires identification of the unit being followed over time. In this example, each treatment plot within a block is the unit we are tracking. The plot column contains such identifiers. Since the number of infected leaves depends on the number of leaves sampled, the range of infected leaves is from 0 to the total number of leaves sampled. This is called a binomial count. We will fit a generalized linear mixed model to analyze a binomial count, taking into account the experimental design. Click the Univariate tab, and then click the GLMM button. In the dialog box that appears, select the infected column as the response variable, treatment, block, and plot as the class factors, and DSE as the covariate. We need to tell Navure the total number of leaves sampled for each number of infected leaves. Use the offset/trials field at the top of the dialog box to specify the leaves column in this field. Click the blue play button to start the process. A new dialog box appears, with a navigation pane on the left containing 5 items. Each item presents different options in the middle pane, while the right pane displays the previously selected list of factors and covariates. First, examine the contents of the Fixed Terms tab. This tab has 2 panes in the middle, Family Options and Fixed Terms. The response variable in a data set is typically a mixture of random variables that belong to the same family but differ in the parameters that characterize them. For example, suppose we have a data set from a 1-factor, 3-treatment experiment in a completely randomized design. When we say that the response variable is a normal random variable, this is true only if the mean and variance are not changed by the treatments. Technically, it is more accurate to say that the response variable is a mixture of random variables that all belong to the same family, say normal. This is what the Family Options panel refers to. The default family is set to normal, which assumes that the response variable is a mixture of normal random variables with the same variance. The variable in question is a binomial count. So, we will select the binomial option. Note that this choice causes 2 fields to appear, namely total count and link function. The total count field is automatically filled with leaves, the column we already declared in the offset/trials field of the previous dialog box. The link function is not an easy concept to explain in a paragraph. But it establishes the relationship between the expected value of the response variable and the so-called linear predictor, thereby accounting for nonlinearity and ensuring that the estimates of the expected values and their confidence intervals will be in the range of the random variable. For example, in a model for binary outcomes, the default link function is logit. There are 2 other link functions that are commonly used for binomial variables, probit and complement log. When you estimate the model, the estimated expected values are on what we call the link function scale. On this scale, the expected values and predictions will be in the real number range, but when we go back to what we call the response scale, which is what we use to report the results, they will be in the 0 to 1 range because the outcome of a binomial variable is expressed as the probability of the event of interest. Let's shift our focus to fixed terms. Our primary interest is to understand how treatments affect disease progression over time and to make a recommendation as to which treatment is most effective in controlling the disease. To do this, either double-click the treatment item in the right pane, or drag and drop it into the fixed terms pane, and also add the covariate DSE, as well as the interaction between treatment and DSE. While our focus is on the treatments and time, it's important to recognize that blocks can also contribute to variation. The complete randomized block design is used to proactively identify potential sources of variation in response variables. For example, we can consider different sites as blocks, each with different levels of disease pressure. Although the difference between blocks is not our primary interest, it is important to recognize it as a source of random variation. Therefore, we'll label it as a random term. To do this, navigate to Random Terms in the left pane and double-click Block in the right list to add it to the random terms. Since the same plot is followed over time, there are correlated observations. To capture this lack of independence, we add plot as another random term. It is important to realize that plot is a nested random term within block. In generalized linear mixed models, this is indicated in two different ways. One is, as we have done, to label the plot as representing different items within and between blocks. The other is to use a syntax that can sometimes be confusing if you are not familiar with it. Navure has a button to add a term nested within others. Since there are two main terms in the fixed part of the model, one related to a factor, treatment, and the other to a covariate, DSE, the question arises as to which of these terms we will focus our attention on to generate the output. If we focus on the treatment, we will use the post hoc means comparisons method. However, the means comparisons are not independent of the covariate because an interaction term has already been included. Therefore, comparisons must be made for multiple levels of the covariate. We want to focus our attention on the progress of the disease for each of the treatment, we should request the output of the model coefficient to be able to calculate some quantities of interest such as the day since emergence at which the incidence of infected leaves reach 50%. We will move on to the strategy of comparing means at different times. Go to the Post Hoc Comparison tab. Select the treatment in the fixed classification terms. This action allows you to select the comparison method, the significance level, the order in which the means are displayed, and the covariate values at which the means are compared. We will clear the decreasing values checkbox in the means display order section. This action will display the lower incidence of the disease in the first positions in tables and graphs. In the covariate values panel, the first entry is set to DSE equals mean, indicating that comparisons will be based on the mean of the covariate. However, since we expect treatment differences to evolve over time, we want to include additional comparison points at 15, 30, and 45 days since emergence. To make this adjustment, click the green Add button at the top of the panel, which brings up a dialog box. Type 15 in the new value field and click Add. Repeat these steps to add 30 and 45. Finally, select the mean value and use the red button to delete it. Click the OK button to close the dialog box. The items in the covariates values are updated. Click OK and wait for the results. This may take a few seconds. Let's explore the output. Below the model title is the R script for fitting the model. If the column names involved in the model contain non-ASCII symbols, note that they have been changed in the script to contain only ASCII symbols. The model summary table provides an overview of the conditions under which the model was fitted and includes key statistics for model comparison, such as AIC and BIC. It also presents the deviance, an important metric that indicates the fit of the model to the data. This metric, when divided by the residual degrees of freedom, dF, of the model, serves as an indicator. Ideally, this ratio should be around 1 for a well-fitted model. A problem arises when the ratio exceeds 1, indicating a phenomenon known as overdispersion. The question then becomes, at what point does the ratio become problematic? While the answer is somewhat subjective, we contend that a ratio greater than 2 should raise concerns, but if it exceeds 3, it indicates a clear problem with the model fit. The ratio of deviance to residual degrees of freedom in our example is about 1.3. Therefore, we can assume that this model is a good fit. The ANOVA table shows that there is a significant interaction between treatment and DSE. This means that the magnitude, or possibly the direction, of the difference between the treatments depends on the DSE, and that the dependence of the response variables on the DSE is different for the treatments. If we scroll down the results, we will find the mean comparison tables and their corresponding graphs when the DSE is equal to 15, 30, and 45 days. The graphs provide a quicker picture of the comparisons. At the beginning, 15 days, only treatment 1, the control, shows a disease incidence that is significantly higher than the other treatments. By the 30th day since emergence, treatments 1 and 2 show a significant increase in disease incidence compared to the other treatments. Note that the no fungicide control has 82% of the leaves infected. Finally, on the 45th day since emergence, treatments 10 and 12 remain the most effective in controlling the disease. Always remember that the charts in the reports are copies of the charts in the Graphics tab of Navure. You can modify this original chart with all the options offered by Navure.